Good afternoon.
Hello.
Well, hello everybody. Let's get started. 12:30. The first thing I wanted to talk about is when you look at some of these answers in the blue book in the problems for test 4, you'll notice that sometimes I show stereochemistry for some of these answers and sometimes I don't. Okay, there's a good reason for that. So when for something like say bromination, Br2, Br2H2O, and the diol reactions, both of them. What you'll find is that only when the double bond is in the ring is it really necessary to show the stereochemistry. So that's the linking factor there. And the reason for that, I'll give you an example. We'll look at halogenation here. So you'll notice in these instances where the BRs are on a ring, I've shown the stereochemistry, but when the BRs are outside the ring or on a chain, I haven't shown it. Now let's look at why that might be. So these are the examples here. You can see that in the first two where I showed the stereochemistry, the double bond is inside the ring. It was in the other cases, they're outside the ring. And the reasoning for that is because when it's inside the ring, there's a clear method for the bromine to have to add. Whereas if it's in a chain, then what can happen is that there's a lot of free rotation that can occur around that double bond, and that can provide more ambiguity for the stereochemistry. So while it's not wrong to show stereochemistry in those instances, it's just that we really can't be that sure of the stereochemistry, or not as sure at least, as the stereochemistry when the double bond is inside the ring. Does anybody have any questions about that? Now for Simmons Smith, you're forming a ring. So let me show you that one just in case you're not familiar with what I'm talking about. There we go. Here's the Simmons Smith reaction. So it forms that ring there. So because it's forming a ring, you pretty much do the opposite. You show the stereochemistry when the double bond is outside the ring. The initial double bond, I'm sorry. See, technically, you really don't even have to show the stereochemistry when the double bond is inside a ring. Unless there's other things connected to it, of course, like there are in this instance, I guess. But if you had something like this, it was just this straight up ring with nothing else connected to it, I suppose you could possibly just draw this, with the justification being that there's no way that this could be anything but cis. So there's no real ambiguity there. But you start connecting stuff to the double bond, and yeah, you're going to have to show stereochemistry. If you look at the answers, I think that's what I've done. But the difference there between the Simmons Smith and the other ones is that you're actually forming a ring, and in those other cases, you're not. There we go, there's Simmons Smith. You can see how I've shown the stereochemistry in all of those instances. Okay, now one other thing I want to point out with showing stereochemistry. Let's say your answer looks something like this. So both of those structures are equivalent. So it doesn't matter which one gets drawn above or below. What matters is whether it's dashed or wedged. That's what's going to determine the stereochemistry. Does anybody have any questions about that?
I would love for you to work out that third one in the list of examples, the Simmons Smith. I know that the answer is there, but even looking at the answers, I have a hard time determining where to put the stereochemistry. Do I put it?
You mean this one here?
Yes, okay. That's a good one. That one or the one below it, either one, but that one will work, I think, for both.
Well, certainly for the ones that are in the chain, you definitely need to make sure that the stereochemistry gets transferred from the reactant to the product. So if it's a trans double bond, you'd expect a trans ring.
But does the stereochemistry go on the actual ring or on the?
Well, it can really go on either. So I'm going to show you.
That's what I was wondering, and it seems like in in the test keys and then this book, they kind of do both.
Right. Well, could be why? Because they can, right? So here are two ways of expressing the answer here for the first one. I can show the stereochemistry by wedging the ring like that, or I could show it this way as well, which I think is the answer that's in the blue book. Oops.
That is the answer in the book.
Right. Okay, so what's the difference between these? In this instance, look at the ring, it's in the plane of the paper. And if you look at this one, you can see everything else but the ring is in the plane of the paper. The difference between them is that you could look at them as being rotated relative to each other by about 90 degrees. Much, I don't know if you can see my hand here, but much like I'm showing you how you're moving your hand.
Okay.
Yeah.
Would the methyl group on the end, in the first one that you drew, would that be a dashed?
No, because it's in the plane of the paper, so I'm actually.
It can stay there. The ring doesn't force it down.
No,
because I think that's what's confusing to me, because in the second one, you did put the ring, part of the ring, down.
Well,
you didn't leave it in the plane.
Well, no, this is the issue, Rebecca. No, I can't see the thing here, but can you see what I've got in the camera?
Yes.
Okay, so that's a triangle, right? Now that's in the plane of the screen, so that would be straight lines if I was drawing it on the paper.
Okay.
But if I did this, now my hand can be in the plane of the paper.
Okay.
That's the difference between them. And which one you choose is actually doesn't really matter that much. Is that all right?
It is. Just maybe one more follow-up question. On the first answer that you drew,
yes.
Does it in this case as well? Is it okay if, let's say, the wedges were pointed down instead of you drew the triangle up?
That would be fine. I could also dash both of them as well. I can't put a wedge and a dash though.
Right.
That doesn't make any sense.
Okay.
It's a three-membered ring. I mean, that's just impossible.
Okay.
From a geometrical perspective. Okay. Any other questions? I had this one. Okay. There we go. Here. No. All right. All right. Let me go through question one and the kinds of questions you could possibly expect to see. So if you look through the old test, you'll see these patterns, but you'll definitely get a dehydration. And by the way, you can always look at the test for reaction list, which is in the blue book, to get an idea of what these are called, right? So throughout those pages from 13 onwards, if you want to look up and see, what is dehydration? Well, you'd find dehydration in the list here, and then you'd go with that. Like that's dehydration. Okay. What else will you get? Yeah, transdiol formation, you'll definitely see that. dehydration. Cystidyl, sorry, the other one's cystidyl, but it doesn't really matter. You get both, you get one of each. Alkyne formation, hydroboration. There's only like 13 reactions anyway, so you'll see most of them. There are some you won't see, like you won't see osmolysis, for example, as part of question 1. I don't know if I can guarantee you'll see Simmons Smith. Just trying to think. Probably, yeah. Let's go with that.
What's the word you said right before this? You said you won't see what?
Osmolysis.
Oh, ozonolysis. Okay.
But you know, you can see that from looking at the old tests. So let me. So it's actually really 2 of 3 if you look through hydrogenation and hydrogenation, poison catalyst. And the bromination, I think that'll be one as well. So yeah, that pretty much, I think that pretty much. That pretty much tells you what you're going to see. Does anybody have any questions?
Yeah, can you star which one of these we need to know the stereochemistry for?
I mean, I can just do it on a general basis, but it's subject to what I said earlier, Jonathan. You know, about whether the double bond is inside the ring or outside the ring.
Right, I
Did
thought
you-
those only applied to the Brahmin or the Br2/Br2H2O and the Simmons Smith.
No, I didn't say that. I don't think I said that.
Oh, okay. So those apply to all of them then?
Not all of them. I mean, look, it's kind of an annoying question. I'll admit it, Jonathan.
I'm sorry.
But I mean, I'll do it, but you know, I do it under protest. Okay. Only because it's an overgeneral question. And they all kind of have their own stereochemical foibles. And you know, then you can talk about hydrogenation. You've got to show the cis, you've got to show the trans. So I'll go ahead and put a star on that as well. But I suppose for dehydration, hydration, and the other ones, I suppose there really is no real need to show the stereochemistry. Plus, you would show it on bromination. But again, only if the double bond was inside the ring in the case of bromination, and for Simmons Smith, if the double bond is outside the ring.
Okay, thank you.
All right. That's probably the best I can do. I'm sorry about that. All right, any other questions about number one? Okay. Number two is going to be a synthesis problem. It's very much like what you did in test 3. I know there's only one arrow there, but it's always going to take, well, for this one, I'll just go ahead and do it. I mean, I'll just go ahead and do the form that's going to take. So in theory, well, not in theory, in practice, you could come up with the A, B, and C by looking at the reactions in question 1. All right, does anybody have any questions about number 2? Because it's the same kind of formatting as what you have for number 3.
Just real quick, when we're looking for reactions from our test to complete the A, B, and C, it always goes forward, right? It doesn't, you can't use a reaction backwards.
Actually, I don't really understand that question, Rebecca.
Well, normally when we're, like when we do the mechanisms, we're always drawing an arrow pointing right. So let's say you were looking for something with bromine and a double bond, but you're starting with the double bond. You wouldn't work backwards with the NaOH, H2O, and heat, correct? Like I have, I don't know which test you're looking at.
Well, it's fall 2019, I think.
Okay. So,
well, I mean,
I'm just saying when you're looking for reactions, you would not use the mechanisms in number 1 backwards. They only go from left to right.
No, I would disagree. I would disagree.
Okay, that's what I thought. But
I mean, for a synthesis problem, what I've always suggested is that you look at this product first,
right.
Find something similar in the products of question 1 and work your way backwards, find what's in the middle, and then work your way forwards.
Okay, no, that answers it right there. That's what I'm saying. It has to be in the products of number 1.
Well, that's where you should start.
Yeah, okay.
But yeah, one other thing I'll point out here, I mean, if you look through the list of reactions in number 1, there's only one that starts with the 2 BRs.
Mm-hmm.
And so you already know. I mean, you already know which reaction that is.
Right.
So you could technically work your way forward on that one.
Right.
And
right.
that might make your life easier, but that's not always going to be true.
Right. Okay.
What I'm saying is I think it's usually foolproof to start with the product and work your way backwards.
Okay.
When writing it out, though, you couldn't write the product as where the BR is, right?
No, absolutely not. No, it has to follow that. It has to follow that pathway.
Okay, I was going to say, even if the arrows are pointing the right direction, you still want it on the right side. Okay.
Right. That's correct.
I have a question, Dr. Musgrave.
Yeah.
So on the reactant, so I was seeing it as OH minus over heat, but in theirs they put H2O OH minus. Does that like?
No, that doesn't really make a difference. I mean, I would, if it was me, I would just copy whatever's in question 1.
Perfect. That's what I wanted.
Right, but this person, it's not wrong to include the H2O because it is in a water solution.
Mm-hmm.
But they probably saw it somewhere else as that, and that's fine.
Okay, perfect.
Okay. Any other questions about number 2? Okay. Now, number 3, if you look through the old tests, you'll see that, well, they're all the same. Every last one of them, it's all the same. I wonder if it's going to be the same on yours. I think so. Okay. Number 4 and number 5 are going to be NMR problems with the where you're given a molecular formula and a NMR spectrum. Number 6 is going to be the IR problem where you're given a molecular formula and an infrared spectrum. You have to come up with compounds that match. both of those bits of information. And number 7 is the roadmap problem, where you have to use those analysis to help figure out what A, B, and C are before you can go ahead and find these other products like D and E. And yeah, these are things we've been through before as well. Does anybody have any questions about the structure of the test or any of the questions you're going to see?
Could you go over a question like question 7, please?
No, let's before I get on to specifics, let me just figure out if there's any general questions anybody has about the test. Okay, it doesn't look like
It's going to be next week, correct?
Next week? What's
The test?
Yeah.
Monday or
I
Wednesday?
think so. Monday, I believe. Per syllabus, Monday. Let's have a look. Make sure I'm not saying the wrong thing here. I'm pretty sure it's next Monday. Yeah, there you go. And then Wednesday will be a review for the final exam. All right.
Thank you.
Any other general questions before I get on to taking requests for things? Keisha, was it you who was asking about number 7?
Yes, it was me.
Just trying to think if just looking at this, see if I did this one. I don't know if I did. I don't think I did. Can anybody tell me if I did this specific one?
I don't
think so.
I don't think so.
I think it was another one. Well, yeah, part of the problem is they all look the same, don't they?
Yes, that's kind of where it's confusing. It's similar, but not really.
It has its benefits, and at least you know you're not going to get anything out of left field, right? Okay, so what you would do is you'd figure out. Now, I do have a worksheet for this as well in the. Let's have a look at that. It's in the test 4 folder. At least I thought I did. Where is it? It's up the top, I think. There it is. Test 4 roadmap exercises, roadmap examples. It's like 7 of them, and they have answers as well. So that's something you can look at in addition to the old test. So you're not just bound to what you're seeing on the old test. Okay. So these would be the 3 products that you get, but you wouldn't know initially which was A, which was B, which was C. All right, so then you notice that there's a whole lot of stuff about ozone here. So, and you've got the actual products of the ozonolysis reactions down here. So you would figure out what each of these would do when treated with ozone. So you would apply that ozonolysis pattern we talked about last week. So the pattern is you break the double bond, that's why I've drawn the lines there, and you put a double bond O on each carbon of the CC double bond. All right, so then the challenge becomes how you reconcile the products that you see in the problem with the products you've made over here. Let me make that one a little bit clearer. So what I would say is, well, you've got this product here. It's actually the same as the product of B. So I know that that's B. The other product that's here is this one here, is a product of C. So I know that that's C, which makes this one A. And then after that, you can go through and you can do the rest of the thing here. So from C to D, so that's C. And again, you'd have to know these reactions to have a shot at being able to get it correct, I guess. But for that specific set of reagents, puts an OH on the least substituted side of a double bond. And what's the other one? That's B to E. And for that one, you probably want to show stereochemistry since you are putting hydrogenation on a ring. Now you can either show the hydrogens or not show the hydrogens, but hydrogens go cis and the rest of it will go up. Okay. Does anybody have any questions?
Yeah.
Made it a little bit clearer.
Okay, I'm sorry, Jonathan?
Yeah, so for the ozonolysis of A, does the other product with the double bond O just get written off as a side product?
Well, it's actually, you don't get A by looking at problem 7 at all, really. I mean, not by looking at the actual reactions, because there isn't a reaction involving A if you look there. So the way it's picked up is by process of elimination. We've found B, we found C, the other one has to be A.
Okay, thank you.
What I'm saying is, what your question doesn't have any relevance for this problem.
Right.
All right, does anybody else have any questions about this one? I think one of the things I'll point out here is that A, B, and C are not these things I'm putting check marks on right here. Those are the products of A, B, and C once you've treated them with ozone. So I think that's a distinction people need to be aware of. It's not very often that people really mess up this question, but when they do, it's because they've made that determination incorrectly. All right, does anybody have any questions? All right, what about any other questions on the test? Any other test questions people want me to go through?
I understand the NMR. I think it's just the beginning when we did it in lab, how we had to figure out like the multiplicity.
Sorry, Bailey.
And like usually when there was oxygen, sometimes it would go up by 10 on like the product side. I never really fully understand. I'm sorry, I'm at an airport right now trying to fly to 6.
Oh, okay. All right, let me see what's going on in chat here. Okay, thank you. All right. Okay. Is it multiplicity you have trouble understanding, or the double bond equivalence? Because I'm not really clear on your question. Can you say either way? You can put it in chat if you want.
Are you able to hear me?
I can occasionally. I can now.
Okay. So during lab, when we did the problem, often when we had an oxygen, it would go up by 10 after, like we just did the very beginning, like when we just wrote out the compound, and then we drew an arrow, and then you write out the rest.
Well, that's that's not multiplicity. That's double bond equivalence. I think that you're talking about.
You find the double bond equivalent.
Yeah, that's not multiplicity. And multiplicity is.
Is it? Okay.
Multiplicity is the number of peaks.
I asked you a couple times during lab, but I never fully.
Okay.
Okay.
So the idea would be.
See, like how we have.
So the idea would be for C13H8O2, we would ignore the oxygen because it doesn't play any part in the calculation. And then what we want to do is we want to figure out how many hydrogens it would have if it was saturated. And we do that using the saturation formula, which is given to you, by the way. It's in the notes you'll have at the end of the test. And then we take the hydrogens and subtract them and divide them by 2. That gives us double bond equivalence. But I think the part that was confusing you was this. That's what it is if it's saturated. It's always CnH2n plus 2. 13 times 2 plus 2 is 28. You can let me know if you understand that if you put it in chat, Bailey.
I think she responded in the chat.
Oh, okay, cool. All right. Okay, does anybody else have any other questions they want to ask? I know it's tough because I know a lot of you haven't looked at anything yet for this. In fact, I'd be surprised if, well, very many of you looked at anything at all. So it's hard to ask questions when you haven't looked at anything yet.
I have a question.
Yeah.
Can you do the asymmetric alkene with the 2 products? One of those questions.
Alkyne, you mean, right?
Yes, alkyne. Sorry.
Well, I'm going to be real transparent here, Deanna. I'm going to tell you that this is what you're going to see on your test. I mean, it's right there. I mean, that's what
Is
you
that
want
number
to see.
3?
Yes.
Oh, that's the same for all the tests. Okay.
Yeah. I don't know if I can be more transparent than that.
No, that's pretty clear. It's either you get it or you don't type thing.
I mean, I can go through and tell you the process, but you know, it's it is. I mean, it is what it is. It's right there. You know. I can tell you some things you need to be careful of. For a start, with the alkyne, you always express that as a straight line compound, and then when it turns into an alkene, it gets turned into something where it bends because it's no longer subject to being straight. And those are pretty much the only foibles you need to be cognizant of, I think. Everything else is pretty much straightforward. It's just, you know, the mechanism of that reaction.
Okay.
Do you have any specific question about Deanna?
No.
Okay.
Dr. Musgrave, can you go over an IR problem?
Who's asking me that? I didn't.
Mariah.
That's Mariah. Okay, thanks, Mariah. Okay. Let me pull up the test here for that one. Because, you know, the reason I'm pulling this up is because the extra sheets aren't with the answers, you know, the key. All right, so that's the question. So first thing you would do is you would look at the double bond equivalence. So it would be C6, H13, NO. Now, per the sheet that you're given here, it's got all the rules and what you would do with nitrogen, for example, and oxygen. For nitrogen, you subtract 1H from the original, so it becomes C6H12, and oxygen doesn't have any effect. And if it was saturated, it would be C6H14. So that would indicate that we have 14 minus 12 divided by 2 is 1 double bond equivalent. So that's what we look at first. Then we would focus on the spectrum, and I'd recommended a little bit of a checklist, which pretty much covers everything, really. And in order to determine if these groups are present or absent, you would focus on the correlation chart here, along with the pictures that you see here as well. And you can see that for the NH2, you're talking around 3,500, you've got this double peak. And that's what we see here. So that would indicate that we have NH2. If we have NH2, we can't have OH as well, or NH. So both of those are going to get eliminated. We also see this big peak down here, which happens to fall into the C double bond O range, and you can see that here, which would indicate that we probably have the alkanes present, but not the alkenes. And the other way of looking at that is you look at these peaks that are around 3,000. If they're less than 3,000, then out of these two, it will just be the alkanes that are present. Does anybody have any questions so far? Okay. Oops. So with all of that, we have to come up with 4 structures that have that molecular formula. and they have to contain a C double bond O and an NH2. They actually don't have to be together, but that might be where I would start. And then I would try and come up with structures then that had that many carbons. So you need 6 carbons. I've only got 2 present now. That'd be 3, 4, 5, 1, 2, 3, 4, 5, 6. So what that there would be a legal compound. And you might be saying, well, how do you know it's got the right number of hydrogens? Well, what I would say is that as long as you've got something that's got the right number of double bond equivalents, the hydrogens take care of themselves. So then you'd probably come up with the 4 just by rearranging something like this, but you don't even have to go that far. You could do something like this as well. And put the C double bond O down here, that'd be different. But if you wanted to mess around with the compound, then you could just branch the chain or something like that. 1, 2, 3, 4, 5, 6. And then, there's lots of different combinations you can come up on top of that. Probably like 20 you could probably draw for that. Does anybody have any questions? Mariah, is that all right?
Yes, that's good. Thank you.
Okay. Any other questions? Does anybody want me to go through anything else?
I wouldn't mind seeing one of the IR questions then. Number 5, we kind of started it.
IR and NMR.
I'm sorry, NMR, sorry.
I think I went through, I can't remember, did I go through both of these? I don't know if I went through this one specifically. I don't think I did. All right, let's do this one. I don't think I did this one before. All right, so we already established double bond equivalence, so C13H18. And then if we're saturated, it would be C13H28. So 28 minus 18 divided by 2 is 5 double bond equivalents, which immediately tells me that I've got an aromatic ring taking up 4 of those double bond equivalents. And you can see that aromatic ring over here in the 5H over here as well. So the way I like to start out is to show the molecular formula and then subtract everything that's in here. So we've got the 5H, which is that C6H5. Now remember, this determination is coming from the sheets that you're given with the test. So that tells you what you need to look at for the integration, for the numbers above the peaks and what they mean.
And that sheet says this is, I mean, this one shows 5H, so this is a aromatic ring with 5 hydrogens attached.
More specifically, it says 5H in the 7 to 8 ppm region.
Okay, yes.
Right,
Okay.
and you can see that pig is in the 7 to 8 ppm region, so it is definitely aromatic.
Okay.
Then we also see CH2. We also see a CH2, and then 6H. And per my guidance, it's a single peak is generally 2 CH3s, and then we've got another CH3 here. Now you'll notice I draw the 6H with CH3s in a vertical line. The reason I do that is because I know that they're going to be related by symmetry because they're under the same peak. Now it's going to sound like Dutch to a lot of people, but that's the reasoning behind it. It's really important. I mean, I think that's a really important concept, a concept of symmetry, and the fact that if something's under the same peak, then they're related by symmetry. What else have we got there? I think that, well, that's all we can see. So I do the subtraction step, and I've got 13 over here, and we've got 6, 7, 8, 9, 10, 11. So I know I've got 2 C's left over. And I've also got 2 O's left over as well. And I also know that that's got 5 double bond equivalents. The ring takes up 4 double bond equivalents, which means there's 1 double bond left over, and it's probably going to be the C double bond O. The important point about these groups here that are the result of subtraction is that they don't have any hydrogens on them. If they had hydrogens, we would have seen them in the spectrum. But since they don't, we don't see them, and that's why we have to do the subtraction to figure out that they actually exist. So in some of the other guidance I've given you, and certainly if you do enough of those problems I pointed out on the, you know, on the Java thing that I made up, JavaScript thing, you'll notice that I often start with what's connected to oxygen as being whatever's at 4 ppm, and that's my only motivation there, is saying, well, that CH2 is at 4 ppm, must be connected to an O. So in that way, I know I've settled it on the O, and I've gotten rid of that CH2. Now, the other thing about the CH2 is it has 3 peaks. So that would tell me that it's next to something that has 2 hydrogens. So the CH2 is actually next to the other CH2 as well. So I've sorted where that goes as well. Then I look at this CH2 over here, and I see it's got 6 peaks, which means that must be a CH2 between a CH2 and a CH3. So I know CH3 must be next to that. And that would be the CH3 that's on the far right side, because that has 3 peaks, which means it's next to a CH2. So all of that fits. So I've come up with, you know, there's not much left over. I mean, you know, you've got the C, we've got the C double bond O, and we've got the 2 CH3s, and we've got this aromatic ring that we have to take care of as well. So it's not really very many ways that I can put the rest of this together. I'll put the C double bond O next to the O, and I'll put in the C, and I'll connect the CH3s to that to make it a bare C. There's really not very much else I can do. And then I can put the aromatic ring on the remaining space. I think I'm pretty much done. I don't think I've missed anything. Yeah. Does anybody have any questions? So a question you might have is, how would I know if these two aren't different? Aren't switched over. I mean, it's a fair question, so I'll address it. By the way, that would not lead to too great a point deduction if you did go that route, because I mean, looking at it at first glance, it could be either really, but there are some things that we can look at that will help that. I'm going to pull up another instance of my courses here so I can show you something. So in the proton NMR exercise file. Also in the PowerPoint notes, I've got this as well. But in this NMR guide, I go through this kind of thing here where I look at what the peak shapes look like when the aromatic ring is attached to different things. And you can see when it's attached to a C double bond O, it tends to get split into two and centralized at around the 7.5 or 8 ppm. Whereas if it's connected to a regular C, it tends to be more a straightish kind of peak that doesn't get split apart. So when we look at this set of peaks, it's not split up. I mean, yeah, you should see the three peaks here, but it's only one grouping of peaks, is my point. So that would indicate to me that the correct one was this one, because this would result in one set of peaks in the aromatic region, whereas this one would result in two sets of peaks in the aromatic region. All right, does anybody have any questions?
I'm going to definitely have to rewatch that. Just, I guess, another question, maybe you were addressing that. Under the 5H, are there two hydrogens next to it or not?
No, because
it's more to do with the shape, like you were just discussing.
Well, part of it, and you remember what I had said about Pascal's triangle?
Yes.
I mean, that's specific when you've got things hydrogens next to each other. If you've got that kind of intensity, as we have in these other peaks down here, yeah, you can make that determination. You can say, oh yeah, that 2H has got 3 next to it. But look at these peaks. Do you see how they're not the correct intensities?
Yes.
To match that. What that indicates is that it's just a whole bunch of overlap going on. So these 5 hydrogens are all overlapping with each other, and they're just close together in the spectrum. So,
right.
So no, you can't make that determination.
It doesn't give you any information about what's next to.
No.
Not like the other Pascal's.
Right.
Peaks,
Right.
Okay.
And what I'm saying, what allows you to make that differentiation is the fact that you're not seeing that Pascal's intensity.
Okay.
I know that's really subtle, but that's how it is. So you wouldn't look at the 5H and say, oh yeah, that must be next to a CH2.
Because it doesn't have the Pascal's intensity.
And besides, even if it was next to a CH2, it wouldn't see them because that CH2 would be too far away.
Okay. Is it obscured by all of the H's in the ring?
Not obscured, no. It's just too far away. Okay. Remember that the multiplicity applies to hydrogens on carbon, right?
Mm-hmm.
So even if you had this situation and you were trying to argue that the aromatic ring would see the CH2, they couldn't because there's a C in between that doesn't have any hydrogens on it.
Okay. Okay.
So that's why that would be impossible. So what are we looking at there with that 3 peak of relatively equal intensity? Well, you're looking at this hydrogen seeing this hydrogen, this hydrogen seeing this hydrogen, this hydrogen seeing this hydrogen, this hydrogen seeing this hydrogen. And yeah, it's all one big mess. And they're all really similar, so they're all pretty much in the same place, but not exactly the same place. So we end up getting just that mess of peaks there, but doesn't obey any form of multiplicity that we've talked about.
Are there 3 lines because there's 3
no
planes?
No, okay. No, there's 3 lines because I put 3 lines of equal intensity so people wouldn't think that it was next to a CH2. That's all. That's all I was trying to say.
Okay.
Now, if I had it would have been really cruel if I'd done this between 7 and 8, because then that would be really confusing. Wouldn't you agree?
I'm laughing and thinking, thank you for clarifying that.
But well, you know, the thing is the aromatic ring, because it's it's subject to so much overlap. It's
Okay.
not really. It's not like it's not subject to the same rules. It's just that it's not as useful to talk about multiplicity with that.
Okay, that makes sense because of all of that moving and looking that you're just illustrating. Okay. It also is helpful to me to just think about, I forget about the C, you know, in between, and that's blocking no matter what. So
it is. Okay. That's true. Yeah. So it's not like there's anything exceptional going on here. There isn't.
Okay.
Right.
All right, and that's why the 3 equal lines, or it could really be any number of equal lines, right?
Yeah, but the other thing I'm trying to be careful of there is not to put it into 2 groupings of peaks like this, for example. See, if I did that, then I'd be thinking, oh, there must be a C double bond O attached to that ring. In which case, I'd be thinking of the other answer here. Do you see what I mean, Rebecca? How I split that into 2 separate peak groupings, but this is just 1 peak grouping. And yes, I could do anything with that as long as I'm careful not to make it look too much like any of these things down here and make people think that there's some multiplicity or something going on, but that wasn't. See, I'm not in the business of throwing in red herrings.
Okay.
Any other questions about this one? All right, any questions at all about anything else on the test anybody wants to ask about? All right, so it is next Monday, the test. And you know, it's the same bat time, same bat channel, just like we've been doing. No, nothing's changed as far as the requirements go or anything else. I'll try and get it graded as quickly as I can. I won't have lab afterwards, so that'll help. And I'll be able to get it done a little bit more quickly, but it's still a bit of a trial because I have to do it, you know, off of the Dropbox, and that means using all those funky abbreviations that I sent out last time as well. All right, any other questions, burning questions about test 4, folks? All right, well, let me put in another plug for the proton NMR exercises, which are in the proton NMR folder, which you'll find in the test 4 folder. And it's under my proton NMR exercises with structure builder. Now, somebody was telling me that they were having trouble getting it to work on their computer. I don't know why that would be. It is JavaScript. All I can think of is that you need to update JavaScript. But yeah, I think they were saying that these links weren't even appearing, but I don't know. I don't know anything about that. As you can see, it seems to work okay right now. Don't forget to always wait about 10 seconds for it to load, because it takes a little while to completely load. All right, so then you figure out the double bond equivalence here. So it's 9, C9H9. If it was saturated, it's oxygen, it's chlorine, so it'd be C9H10. If it was saturated, it would be 20, so I think it'd be 5 double bond equivalents. So if double bond equivalents are correct, then we figure out the pieces. So we've got a 5H aromatic over here, which is this one. And you'll notice it counts down here. And we've got 2 CH2s, so we pick that. And then what have we got left over? We've got a C, an O, and a double bond equivalent. So that's a C double bond O. Check the pieces, see if they're right. Oh, they're wrong. Wonder why they're wrong. Oh, I know why. I'll reset that. I missed out on the CL, didn't I? Let's try that again. See? That's how you'll do it. So C double, let's see, the two CH2s, C double bond O. And there's a CL over here as well that's left. So I need to take account of that too. Where is he? There he is. All right, check the pieces. And now they're okay. So the anchor goes on the anchor piece. And then we have to put this together in such a way that it's coherent. The two CH2s have to go together because they both have 3 peaks. It also says that leaded pieces need to be in alphabetical order, left to right. So I have to put the A here and the B here. And the only way I can really set this up is to put a C double bond over here and a CL over here, and then it's done. Now, if you had doubts about how you got that, then you can watch the video solution as well. All right, so there you go. So you should try and have some fun with that. I would say if people do all of those, I can't really see how you not understand what you need to do on a test with the NMR. You know, I put that together for a reason for you, not just so it can sit here and look pretty. All right, any questions? Anything else anybody has for the test 4?
The naming for the naming quiz, that's going to be in the first lecture that we did, right?
It is.
Okay. I was just trying to remember.
I think there's a video for it too.
Okay.
Is that you, Sierra, talking?
Yeah, that's me. I was just trying to remember. It feels like a while ago.
Oh, it's another lifetime. Let me see. Let me look. Yeah, naming of alkenes and alkynes. So there is a video here that goes through that. I don't think you'll find it nearly as difficult as the previous one, the one we did for alcohols, ethers, and epoxides.
Yeah, that one was hard.
This is not so bad. You know, you could watch that video. I think it's only like it's less than 5 minutes.
Perfect. Thank you so much.
I think.
5 minutes, 10 minutes, 20 minutes, whatever. It doesn't matter really.
There you go. 5 minutes and 41 seconds.
Thank you so much.
I think you could probably handle that. Okay. Any other questions? Don't forget to do the naming quiz. I know some people have already done it. Any other questions? Any other questions? Because if you don't have any other questions, I'm just going to.
There is one in the chat.
Oh, it's one in the chat, Lord. Thank you. I appreciate that. Oh, sorry. I didn't mean to stop sharing. There's a name for people who don't share. Here we go. Do we have class Wednesday? No. We do not have class Wednesday.
I have a question about lab for the last day worksheet.
Yeah.
You dropped the lowest lab grade, right?
Well, that includes the worksheet though.
Oh, so we still have to do it?
The worksheet's a lab. But yeah, well, you only have to do it if your current grade is less than A. But that's even up to you.
Right now.
Well, then.
I have an A. I have like a 98.
Then what are you worried about?
I was just making sure because I was like, do I have to do it?
No, look, if you've already look in the grades, if you've already got an A, you don't have to do it. Even if you've got a B, you don't have to do it. But you might want to do it if you want to try and get an A.
Okay, thank you so much.
All right.
Dr. Musgrave, with so many details, we just like to not just double check, but triple check to make sure.
Yeah. Yeah.
We do it all the time, sorry.
Yeah. Yeah. All right. Any other questions? Anything else? Anybody has? Any other burning questions? It depended on your grade, Bailey. If you've already got an A, you don't have to. If you've got a B, you might want to. Yeah. In lab, we're talking about. Yes, Bailey. All right. Anybody else have any questions? Thank you, Victoria. I appreciate you transcribing for me. Any other questions? All righty then. Well, good luck with the review and the studying and everything. I would try and get as early a start on it as I possibly could. I wouldn't wait until Sunday to start on this stuff. It's you know, some of it's pretty involved. You certainly want to get that naming quiz out the way. I would definitely do that. Okay. Well, good luck, everybody. I'll see you soon. Have a good Thanksgiving and stay safe and socially distant. All right. I'll see you all later.
Dr. Musgrave, can you look at one thing real quick on my video and just tell me if I got it right or not?
On your video.
Hang on one second.
Oh.
I got it. No, okay, there we go.
I can't. You can't share if I'm sharing. Is that what you're trying to do?
Yeah, something like that. Here, I'm sharing my screen.
Okay, now I'm looking at it. Okay.
So these top two that I drew were on the key, but I drew the big one in the center and the bottom. Is that the same? Is it backwards to you? I'm sorry.
No, it's not backwards. I'm just looking at it. All of those are the same.
Okay. I'm just having trouble with the little legs. So I just wanted to double check. Because my answer was this one down here.
Which is fine.
Was on the key.
Yeah, but that's fine.
They're the same. Okay. Sometimes when I'm grading myself, I don't know.
I know. That's part of a challenge.
Yeah. Okay. All right. That's what I wanted to know.
All right.
Thank you so much.
Okay. No worries. Victoria, did you want anything?
Oh, well, I wanted to ask a question that you, I think, answered 3 times already, but I still missed the answer somehow. Okay, sorry. So the question is, do we need to know the mechanisms, or do we not? Or do we want to, we get the points for them?
Yes,
just like
the latter, yes. The last
just
part
like the lab test?
Yes, that's right.
Okay, that's it.
There's only one mechanism you have to know, question 3. Yes. That's it.
Yes, correct. Thank you. That's it. Bye-bye. Happy Thanksgiving.
Thank you, Victoria. Bye-bye. Julie, Adriel, they're all gone. Okay.